Hey everyone, I'm Panji Brotoisworo, a university researcher under the Stamina for Space program. Our program is primarily focused on managing the Diwata satellites. However, we also focus on general remote sensing research and analysis to build the Philippines' remote sensing capabilities. In this case, I will be presenting about our open source software which simplifies the complex process of analyzing ground displacement using radar interferometry. Our software is a front-end tool that relies on Sentinel toolboxes, also known as SNAP. Our workflow uses free data from the Sentinel-1 satellites, which enables it to be used by anyone. Here's the outline of my presentation today. We are including a brief introduction to radar remote sensing so that we can have a little context on how radar interferometry works. After that, I will give a brief lesson on radar interferometry. Then I will talk about interferometry applications in disaster assessment. Then, the last section will be showing you guys the different features of the software using some sample data from the Taal eruption that happened in January 2020. Let's start with a quick intro to our software. With this DInSAR software, we aim to create an easy-to-use general research tool that can be used by fellow remote sensing researchers. We use a completely free and open source workflow using Python, which allows you to perform your own interferometry analysis for free. The default parameters can get you started with radar interferometry. However, we give you the option to modify the parameters to suit your analysis. So these include many different options for filtering and tiling, performance-related options, how much RAM you want to include. We want to make it as flexible as possible, but if you're not familiar with this, again, the default parameters will still work fine. So one of the reasons why we made this software was the Python API for Snap has limitations with which Python version you can use, as seen in the picture. So the latest version you can use is Python 3.4. That's actually quite old. So we wanted to future-proof the workflow and make it really flexible with if you want to include other new libraries. And so to do that, we just modified the XML graph instead of using the official Python API. For those who are not familiar with the XML graph files, these are used by Snap to create automated workflows, and you can easily create these within Snap. So we created a interferometry workflow, which was provided by the European Space Agency during one of their online training sessions, and we simplified it to only a few clicks. For those who want to use it in a server environment, we also developed a full command line interface that allows it to be used in a high-performance computing environment such as the Core HPC, which is managed by DOST ASTI. In addition to the source code itself, you can easily access the XML graphs we created and use them within Snap. This allows researchers to experiment with new parameters and settings which may not be available in our software. Whenever you run an DInSAR analysis, the software updates these XML graphs so you can simply load the graphs, which are saved inside the software folder. An important thing to note is that testing and development was done using Snap 7. We realized that Snap 8 was recently released this month. Unfortunately, it's not compatible. We did some testing. So for the meantime, we recommend that you use Snap 7 only if you want to use our software. So let's talk about radar remote sensing. Radar is an active form of remote sensing. I think people may be more familiar with optical satellites such as Landsat. Those are passive forms of remote sensing. So what's the difference between passive and active remote sensing? Passive remote sensing, it's called passive because the sensors only receive the data which come from the light of the sun. However, in active remote sensing, which is radar. Radar satellites generate their own microwave signal, which reflects from the ground and then back to the sensor. As an example, you can imagine being in a dark room with no windows. You need some light, and you do not have any passive light coming from the sun. So you use a flashlight to illuminate the room, which comes from you. The light bounces off the surface of the room and then comes into your eyes. This is how radar satellites work, except you are the satellite, and in this case your flashlight is shooting out microwave signals. This type of remote sensing is useful because it allows radar satellites to gather data despite cloudy conditions, and depending on the wavelength, they can even penetrate the ground to capture shallow features. Radar is a single channel image, so the brightness in the image depends on the intensity of the radar signal that is returned from the ground. The more intense the return, the higher the value. Radar interacts differently with many ground features. Water often has the lowest intensity because the radar signal gets reflected by the smooth surface of the water. Areas that return a lot of radar signals are often urban areas. You can see in the image that the signal also gets amplified because of the double bounce. So this leads to urban areas looking really bright on the radar image. Vegetation can vary because there can be different types of vegetation. So now that we have a brief introduction into radar, let's talk about interferometry. So you may come across these two terms. There's DInSAR and InSAR. What our software focuses on is DInSAR because our workflow is able to generate a displacement map. But with InSAR, you're only looking at the interferometric image. So that's the phase image, which is the rainbow image you saw in the previous slide. So with radar interferometry, you need two images for it to work. You need one image that is before the event, and then you need another image that is after the event. So let's say, for example, we're looking at an earthquake, and you want to see where the ground sank and maybe where it rose. So because of the way the radar satellites use the microwave signal to get imagery, you can then detect the changes in the phase signal. As you can see in the image, the green color is the signal that was detected due to ground subsidence, and then the red signal is the one that happened before. So you can see that there's a bit of phase difference, and this is the important part of how radar interferometry works. Another important feature is when you're looking at radar data, you often see this feature name in the metadata called the direction of the pass. So there's ascending and descending. So this can actually really affect your data because radar is a side-looking sensor. So because of that, and the way you're looking, or the way the satellite's looking at the ground, the image will look different. The output will be different depending on whether you're looking at ascending or descending. And this can really vary from area to area because of radar distortions. So in the image, you can see that on the left there's the output from an ascending pass. You can't really see the displacement in the phase imagery, but in the right image, which is descending, you can see that there's the circular pattern, which is where the displacement is. It's more obvious. So when you're looking up interferometry, you'll often see images like this. So it's rainbow images. How do you really interpret this? So this is what we call phase imagery. And this shows the phase differences between the pre-event image and the post-event image. You can see that what we call fringes, so that's basically like one cycle of the rainbow, and that depends on the wavelength of the satellite you're using. So in this case, we're using Sentinel-1, and Sentinel-1 has a wavelength of 5.6 centimeters. So it's C-band satellite. So you can see that one fringe, the length of one fringe is equal to 5.6 centimeters of displacement. So you can see that the center of the image where it gets incoherent and fuzzy, that's where most of the displacement is, but due to incoherence, the data is also not really reliable, but you can see that the trend of the fringes show that that's where the displacement is going, because the fringes get tighter and tighter as it goes to the center. For coherence, I was mentioning in the previous slide that the center of the image was incoherent. So, in short, coherence is the reliability of the data, and this is based on the scattering characteristics of the target. So, if the coherence of the data is low, that means it's not entirely accurate, but if it's high, like it's bright, and you can see it, which are often associated with urban areas, then that means it's very reliable data. So when you're working with coherence imagery, you often want to mask out images that are maybe 0.4 or lower. But there's really no hard rule on the lower limit of the coherence. It depends on the type of research. But for me, I use 0.4, 0.5 to only get the reliable data. So in this phase imagery, this is just a phase image of Taal. This is not the eruption, but you can see that there are certain areas where the image is a bit fuzzy, which is highlighted by the red boxes. So those are incoherent. So interferometry is often used in disaster monitoring and assessment. So this is a quick section on how you can use radar interferometry. So here's one of the examples. You can use interferometry to monitor volcanoes. So this is Mount Etna in Italy, and you can see that the mountain or the volcano is changing shape because of the magma underneath. So, for example, this could be applied to Taal, where you can monitor remotely and safely, where the ground is rising or sinking. Another way to use interferometry is for monitoring potential landslides. So maybe in this case you can see that this cliff has an unstable slope, which is in the red color. So that means that this area of the slope has more displacement compared to the others. So that's really dangerous, and then that's more risk for landslides. So if you had something like this, you can have something like an early warning signal. Here's another application. So you can monitor groundwater extraction and ground subsidence because of groundwater extraction. So this is land subsidence in Jakarta, Indonesia. It's it has an issue where their city is sinking because of groundwater extraction. So you can see here that near the coast, there's actually it's sinking. It's sunk by 4 meters. So let's go over a sample workflow. In this case, we'll be doing an analysis of the Taal eruption that happened in January 2020. These are the common requirements if you want to perform the analysis. So these are the recommended specifications, but the minimum requirements I would say are an i5 and 8 gigs of RAM, but that means the total duration for the processing might take a few hours at that point. It's very intensive. And these are the scene details associated with our analysis. So it's a single look complex product type, interferometric wide swath as acquisition mode. It has a descending pass with a right pointing antenna. The orbit number is 32. So we provide the training data, but for instance, if you want to download your own imagery, there are 2 ways to do it. The first method is using the script called download_cli.py. You need to have an account at the Copernicus Open Access Hub, which is where you can get free Sentinel images. So once you have an account, you can use the command line interface and then input your username and password, and then you can filter the results by specifying a start date, end date, output folder. You can filter it by the pass direction, and of course the geometry used for the AOI. All this is stated in the documentation. I won't really go over it in depth over here. The other method is to just go directly to the Open Access Hub and download the images from the website. In this case, you can see that the 2 images we want, they're right there, nice overlap. It's important to note that images need to be from the same orbit number or basically the same region for this analysis to work. In the images, you see that there are 2 black boxes, so they can be used together for interferometric analysis, but the black colors can't be used with the blue colors and red colors. The data will not be valid. And that brings up an important limitation at the moment, because the workflow is currently designed to work with single images only. So this is a problem if the AOI you're interested in is at the edge of the image. So usually the strategy is to just merge the adjacent images together from the same pass. But currently our software doesn't have that feature, but we're planning on including that in the future. Something like this happened during the Masbate earthquake. So it required merging because the earthquake happened in the middle of two images. So it required a total of 4 images, which is around 20 gigabytes of imagery. Okay, so let's say that you have the tutorial data. All you have to do is load the pre-event image in the first line. You can browse for the zip file and then load the post-event image in the second line. The third line, which is shapefile processing mask, is the processing mask used for the phase unwrapping process. The phase unwrapping process is the most resource intensive part of the analysis. So if you want to just focus on a single area or small area, you can put that shapefile there. The fourth line is the output directory, so this will be the directory where it'll save all the output, which includes the TIFF files, but it also includes the .dim files, which you can open in Snap, so you can check all the metadata, all the other types of data that were generated during the analysis. So that would be useful for research purposes. We didn't delete any of that. Lastly, we give you an option to skip the phase unwrapping process. So for people with weaker computers, maybe you just want the phase imagery, you can just check the box at the bottom and it'll skip the phase unwrapping process. So once you press process and confirm, it'll just run the analysis in the terminal and you can monitor it. And then that's essentially it. All you have to do is wait at this point. Once the analysis is done, it'll generate a displacement map similar to this. So you can see that the blue areas indicate regions where the land sank, like negative vertical displacement. Meanwhile, the red regions indicate positive vertical displacement. So we provide you with two displacement imagery. So one is line of sight, but we also provide a vertical displacement map where it's in vertical units instead of line of sight units. The TIFF files that are generated include phase, displacement, coherence, intensity, and topophase. Usually the only relevant imagery is phase, displacement, and coherence. I've never really used the intensity and topophase, but they're there because they're generated as part of the analysis. So these are the details for the software. The software is currently hosted on a Google Drive using these links. The tutorial data includes the zip files because I think Sentinel-1 data is only available for a year, if I recall correctly, on the Open Access Hub. And if you guys have any comments or feedback or report bugs, or you want to suggest improvements, you can email me at pbrotoisworo@staminaforspace.upd.edu.ph. This is the end of my presentation. Thanks for watching.